Hi everyone, it's great I could talk to everyone here. So I'm Jacob Smith, postdoc at the University of Cambridge, but I'm part of a team and there's many collaborators as Dave introduced really. So I'm looking forward to talking to you about the research, the development and the operations of wheat rust forecasting. Right. So jumping straight to the background in the modelling, the research behind that, and then how that's been put into forecasting and operation. Look at a bit of the analysis of those forecasts. Now we have many years of that. What insights do we have? And then I'll briefly show some of the different developments that are also on the way as well. It's just a sort of overview. But okay, so the models we have for the pathogens of stripe rust, stem rust, and leaf rust, we're following the aerobiological framework for the spore dispersal and the spread of disease that way. So from production in infected sites based on field surveillance, there's weather conditions that drive the spore release and the escape from the canopy. And then once they're in the air, there's a number of different meteorological processes that are at play to transport them, spread the spore clouds, dilute them, and move them around in the different parts of the atmosphere. The spores are also subject to viability changes, so exposure to UV, possible impacts from humidity and temperature on the way. So those are other aspects that need tracking. And then how they return back to the ground. There's several different deposition processes. There's dry things like sedimentation and impaction, but then also wet processes with scrub out from rain, for example. So there's a myriad of processes there too. Once the spores might arrive on any susceptible crops, we then need to think about the environmental conditions for infection to take place, the various stages. And then from there, there's a latent period before we might see signs of infection in the field. So we have a series of model components that focus on some of these areas. I'll come into them. So firstly, the 3D spore dispersion model we have. So here's a 3D visualization of what some of that might look like. So this is just for a single stem rust site that was seen in Pakistan in 2018. The black points give an indication of the particles being tracked, which are representing a quantity of spores that will change over time. And the coloured cloud gives some idea of the density of spores that are being tracked through the atmosphere. And so you see there's very complex patterns in terms of how they move. You couldn't have a simple Gaussian dispersal kernel or anything. Like there's wind currents in different directions at different times of day or over the days. Sometimes you see them rising very high up. That might be deep convection going on. Sometimes you might see sudden loss of them from the atmosphere as they're being deposited, or you see gradual deposition, and you also see that there's very long distances involved, hundreds going on to thousands of kilometers. So that's just one site, but then what if actually you're thinking about the broader landscape and the total inoculum load? So this is a case study for a single month based on stripe rust surveys that are fed into Rust Tracker and looking at the ensuing deposition that the model's pointing to. So over the 3 hourly time steps, you can again see several different features going on. There's like daily pulsing of deposition load. You've got lots generally around source sites, but you can also have sort of uneven clustering of deposition away from them as well. That might be the wet deposition going on. And again, you can see some long reach. And yeah, so thinking then about what that regional connectivity might be, we've run some sort of historical analysis over the last decade or so and looked at, okay, what sort of regional connectivity is there based on, if you divide up the source regions based on different, with the blue highlighted areas there, different source regions, here for stem rust, what is the reach of spore deposition? So for example, for southern India, there's clear reach across northern India and neighboring countries, and northern Pakistan, actually that can reach, the winds carry it southeast sometimes, and it can reach as far as Bangladesh potentially. So there's a clear sense of regional connectivity here, and even potentially reaching across the Indian Ocean. So there's an earlier study there. So looking at the principal migration routes and the communities for stem rust connectivity in the area. So an earlier work within the group, Meyer et al. So they'd run a network analysis based on representative disease locations across South Asia and East and South Africa, and they looked at the host susceptible periods, pathogen dispersal for stem rust, and environmental conduciveness to find some messages about the principal migration routes, and so there's several different things going on here. So each of the circles represents a representative disease location that was run. This, the thickness of the lines indicates the amount of spore load being transmitted between those sites. The size of the circle indicates the amount of spore inoculum moving around for that site. The dark shaded region is the amount of spore load moving out of that site, and the light shaded region is the amount moving in. So there's several different messages coming through. There's sort of 5 strongly connected zones with a high degree of spore transmission within them, but also between them. Nepal, for example, with a larger shaded region, it's a net donor, and Yemen's a critical stepping stone between Asia and Africa for stem rust dispersal. And also to point out, I mean, like Dave was showing as well, like the Himalayas are a clear center for genetic diversity for stripe rust, and Ethiopia is for stem rust. So we can start to get a sense of where disease might spread. So with that, okay, we've got these models to look at how wheat rusts might spread. Actually, what do they look like if we're trying to use them as forecasts and try and give some sense of risk estimates for rapid in-season response. So as it is, as Dave has mentioned with the early warning system, so it's now covering about 8 countries with a potential for a few more. So Ethiopia, Kenya, Tanzania, and Zambia, and Bangladesh, Bhutan, Nepal, and Pakistan. And there's some potential there for Uganda, Zimbabwe, and Afghanistan already. And the part on the right just gives some sense of what the horizontal resolution of the outputs are. It's sort of roughly 10 kilometers. And yeah, so from this, so David mentioned about 600,000 smallholder farmers being reached in Nepal and Bangladesh, and there's some numbers for Ethiopia as well. The system is estimated to be reaching more than 850,000 smallholder farmers as well, so there's a big impact there. And so David also shown sort of the broader connectivity between the different types of surveillance going on and dissemination, but here focusing more on what's going on around the forecasting. There's a series of different inputs we have, and then there's several different component disease models that are running for the environmental suitability for infection, spore availability based on field surveys, the ensuing spore deposition, and then the integrated epidemiological model as well. We then generate a series of outputs, those are risk maps and then advisories, and there's various different communication channels. As David touched on, there's translated advisories, but there's short messenger, there's text alerts. Ethiopia put it out on social media, I think, now with Telegram. There's phone-based query hotlines as well in some countries, and sometimes we've heard it's gone on radio and television, which sounds fun, but also extension agents are a real key mode of communication as well. That's also come from the impact studies. Just to give some sense of what the inputs are, if you're thinking like, okay, what does it actually take to set this up and run it somewhere? So this is all driven by state-of-the-art weather forecasts from the UK Met Office. It's provided daily, updated daily for the next 7 days, roughly 10-kilometer horizontal resolution. We have 3-hourly time resolution. That's available to us globally, but we've been focusing on these areas for now. We have host distribution maps that are based on map spam, but then also some expert opinion about timing and some adjustments on it. And then the really key and central part, as Dave says, is the field surveillance, and that it's provided in near real time. So one major change, like during the concept, the pilot phase about 7 years ago, was that it was starting to move from paper-based field surveys to a consistent digital-based phone app field surveillance. That's gone through ODK apps and is now at the Wheat Rust Toolbox with a global rust reference center, which makes a big difference. And near real time means that if there's a surveyor in the field making a record and they upload it, that will be within the model forecast within 24 hours. It will be there the next day. So it really makes a big difference. We've also set up a sort of online news media scraper to try and establish proxy surveys when they're not available in near real time, such as we had been doing for India. So what are the different forecast products coming out? So from feedback over the years, feedback's an important part of this. We've had 3 monthly meetings. So to have sort of have slightly separate forecast products rather than just a single total integrated one. So based on the aerobiological framework from earlier. And what I'm also showing is actually a series of every day's forecast for Ethiopia in last year. So on the left is the spore deposition forecasts, which is capturing sort of the aerial dispersal component from known sources of infection, which are the little red points in the map. Then we also have separately the environmental suitability for infection forecasts, and then putting those together along with knowledge about the host landscape, we have the integrated risk of stem rust infection. And yeah, to reiterate as well, so with the 7-day weather forecast and something along the lines of 14-day latent period, of course that can change a bit in different settings. That gives farmers and the whole system roughly 21 days for rapid response within season. How do those messages make it to farmers? So all the forecast products are put up on a basic dashboard where you can scroll through dates and you can filter for the different outputs and diseases. We also provide all that in a Word document format, so it's immediately there, also with some automated survey analysis and impact tables. And then that means it's ready for expert editing for local context, things that you can't really automatically put into risk alerts, thinking about what the state of the crop is, or what other weather conditions there might have been, or aspects to do with the pathotypes or the cultivars that year. And in many cases they'll be translated as an immediate next step before being transmitted further. As part of the Disease Early Warning Advisory System project, there's been national capacity building as well to help build out ability in different countries. So we've had rounds of training on introduction to the models and interpreting the forecasts and drafting advisories as well. So that's been really great. I was also wondering how many of those who are attendees would actually be here today, but actually I think it is a surprisingly separate group. There are a few who would be presenting, but so it's really, really great to be able to talk about that. So I didn't really say it. So the forecasting was in pilot phase in Ethiopia around 2018 or so. So that's many, many years ago now. It's been in operation in more and more countries now. So what insights can we get from many years of forecasting? Just giving the overview, I'm not actually going in the details, but so there's some consistent messages, like the environmental conditions shift seasonally and differ by altitude, so it often makes sense, which is great. And the signs of long-distance dispersal between early reports of infection when they make it into the system compared to later outbreaks as well, so that's often reassuring. Then we've also run validation studies based on it, looking over the historical period, so it's not strictly forecast analysis there, but on the historic period, we see that forecast skill really benefits from assimilation of those surveys in near real time and accounting for long-distance aerial dispersal, while there's other forms of long-distance dispersal, like the predictability really benefits from having that part of the disease spread in there. And I've also run this sort of validation process on the actual forecast, the series of forecasts of the integrated epi model, and get similar performance, so it's showing that it's behaving as well in the forecast mode as it is in the historical analysis, which is great. There's been a series of success stories, as David touched on for most of them, so the system and the forecasting's credited with support during the intervention on PSTS-16 incursion into Ethiopia in 2021, and also the appearance of a different race of UG99 in Nepal. The forecasting was immediately available to help look at onward dispersal risk. In fact, actually, it was already running on the site before it was even aware that it was stem rust. So the automated system was really working really smoothly. So there's been growing demand, and the feedback has gone really well, and it's now operating in 8 countries, and it's now sort of adaptable and flexible to expand and change to other geographies as needed too. And we've brought on extra diseases, so wheat leaf rust wasn't there 7 years ago, but it came in pretty easily. And wheat blast, there's been a separate forecasting project there for Bangladesh, but it's coming in as part of this project as well. And I'll just touch on some of the further developments that are going on. And that's probably about it. I don't even know how time's going. So in the background, as is often the case whenever you're working with code, I don't know how many people would have thought of that with networking event yesterday, who's learned to code and who's had broken bits of software. Always revising it in the background, and so it's aligning with coding best practices, but what's also crucial is it's gone from a research piece of software to operations, but now actually we need to make sure we keep it separate as well so that you can do them both at the same time and complement each other. That's been really great. Easy is maintenance because that makes everyday life easier, but also making it more efficient and more adaptable. It's really shown that's really helped. So it's been very quick and easy to set up in other areas as demand has come on. We've also been transferring the Wheat Blast forecast model that was running for Bangladesh to run in Zambia. It's a work in progress right now. We're just getting some of the kinks sorted out in the background, but that's going really smoothly. We'd set up an online news media scraper, as I mentioned, to set up proxy surveys. That's been a really helpful tool and interesting to look at how you can sort of fill gaps in the landscape. We're also looking to set up the spore dispersal forecasts rather than just working on just stem rust generally or stripe rust generally, to also automatically pick up when there's a suspicious new pathotype picked up in the sampling or just being queried by a field surveyor, that actually it'll be set up as its own individual forecast, so you can directly look at just the spread of that one pathotype. And also as a separate project, David touched on, and I think Gerald will talk on a bit more anyway, you may or may not, but Gerald has been working with us on it, is to actually look at improving on the maps, spam static maps, by trying to set up wheat maps from satellite observations. A key benefit there might be that they're dynamic, if that runs smoothly. So here's an excerpt from the first study area in the southern wheat producing areas of Ethiopia. So we've been looking at the impact of that on the forecasts. I think that's about everything. So in summary, the early warning system's been set up. Dave really covered it really well. Reaching over 850,000 smallholder farmers, and the forecasts provide, around about 21 days to provide rapid response in season. And it's a really underlying thing that actually app-based field surveillance with like a consistent set of questions and entries has made a really big difference to being able to run forecasts and make that useful. So and this is where I'll mention that actually it's not just me, there's a whole team at Cambridge. So there's Chris Gilligan, Thomas Mona, Will Thurston, Lawrence Bauer, and lots of past members as well. And there's so many collaborators and project partners in country and through the DEWAS project that really make it possible. This slide almost looks like a carbon copy of what Dave had, but for the odd logo switch around. So really thanks to everybody for making it work. Thanks.